Let us look at another way of visualizing a group in the form of a table called the Cayley table. So a Cayley table is a square table that shows the result of the group operation between every pair of elements in the group. Can also be used to figure out whether a set under a binary operation forms a group or not, provided we know whether the elements of the set are associative under the operation. The second part of the statement is because with this table, we can't figure out associativity, but the rest we can figure out. So let's see how to build a Cayley table. The first row, first column shows the operation that is being carried out. The row from the second column shows the elements of the group as labels or headers, column headers. First column from the second row shows the elements of the group as labels or row headers. Each cell in the table is filled by carrying out the defined operation on the row heading and the column heading. Each row column contains each element of the group only once. And the second column and the second row matches the group elements. So keeping these steps in mind, we build the table. So let's actually do this with respect to the two groups that we have already seen. Remember 12-hour clock and the symmetries of the equilateral triangle. So let's look at the 12-hour clock first. Okay, here first row, first column shows the group operation. The first row from the second column onwards, we write all the group elements. That is the elements which are there in H. And ideally, we should put the identity in the first column. Then we repeat that exercise for the first column, again starting with the identity. Okay? And now we carry out the operation. 0 addition modulo 12, 0 is 0. 0 addition modulo 1 is 1. So if you notice, these are just repetition of the column headings. Similarly, this is repetition of the row headings. Now, most of it will be pretty straightforward. The only thing you have to be careful about is 1 addition modulo 12, 11 is not 12, it is 0. 2 addition modulo 9 is 11. 2 addition modulo 10 is not 12, it is 0. 2 addition modulo 11 is not 13, it is 1. So keeping this in mind, you fill up all the cells of the table. Now, once this has been completed, then let's see how our axioms of a group can be looked at. How do we figure out closure property? Remember, closure property says if A addition modulo 12B is equal to C, then C also is in H. So basically what this boils down to is that if you go through these cells in the table, there should not be any element which is not part of the group. Suddenly we should not end up with 12 or 13. So if all the values that are there in this table are there in H, then we can say it is closed. As I mentioned before, associative property can't be figured out directly here, because to establish associativity, we need 3 elements, whereas here we only have 2. Let's say this is A. So A is equal to 0, 1, 2, 3, 4, 5, 11. Similarly, These are B. Now what about C? So because of that, we can't figure out associative property easily here. Okay. Now let's look at the next one. Next is existence of identity. Now here, what happens? If you look at this, all these elements, what is happening here? Here E additional modulo A. So although I mentioned A here, but in this case, let's take this. So all these values are being repeated here. That means E, which is 0 in this case, addition modulo 12 A, any of these is A itself. Similarly, any of these addition modulo 12 0 gives the number itself. So that shows existence of identity. What next? Next axiom is existence of inverse. What does it say? A addition modulo 12 A inverse is equal to E, which is in turn again equal to A inverse addition modulo 12 A. So the way we figure out this is, let us take an example. So let me bring this here. Let me randomly put it here. 5. What is the inverse of 5? Just keep going across the row till you reach the identity. Then 7 is the inverse of 5. What is the inverse of 7? You go to 7, keep going till you reach the identity and see what it is. So 5 is the inverse of 7. Like that, you will notice that every element has its inverse. So when we say the inverse of 5 is 7, we are talking of left-sided inverse. Now when we say 7, we are taking the same example. For 7, it is 5. For 5, it is 7. So basically this boils down to left-sided inverse and right-sided inverse. And these two inverses should be equal to each other. By just these 4 properties, of course, associative property we'll have to figure out in some other way. But if these properties are satisfied, we can say this forms a group. But if we want to also figure out whether it is abelian group or not, that is, we have to figure out commutative property. A addition modulo 12B is equal to B addition modulo 12A. So here, just focus on the main diagonal and see whether it is symmetric across the main diagonal. Let me remove this. So here you have 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 5, 5. Go through it till the end, and if the numbers appear in the same order on the other side as well, then we say it is symmetric. And if it is symmetric, then the commutative property is satisfied. So that is with respect to our 12-hour clock. Now, what was the other one that we saw? The other one we saw was the symmetries of the equilateral triangle. Remember this? So here S is equal to, these are the 6 symmetries of the equilateral triangle, and composition is the group operation. So group operation is written here, and we write down all the elements of this group. Similarly here as well. Again, generally speaking, we keep the identity as the first column in the table and the first row in the table. Now here, remember, E means what? Identity means what? Rotation by 0 degree. Okay, so let's repeat this exercise again. So we go through each of these cells and see whether any element is there in the table which is not there in this set. If there is, then it is not a group. So here, all the cells are occupied by values which are there in this set. So it is closed. Associative property, we can't. Existence of identity. Again, if you notice, E times E is E, E times R is R, E times R square is R square. So again, we have this and this, which tells us that identity exists. What about inverse? We have already seen how to figure out the inverses. Go to each element, go across till you reach E, and the column heading will be the inverse of the row heading. So R, go forward till you reach E, column heading, that is R square, is the inverse of R. For R square, keep going till you reach E, then R is the inverse of R square. Like that, you can figure out the inverse of each element. So that is existence of inverse. If you do this, you will notice that for every element in this set, there is a inverse. Again, for commutative property, we have already seen, just focus on the main diagonal and see whether it is symmetric across the diagonal. So let's see, R, great, R square, great, S, E, S, great. Now what happens to the next one? R composition S, R square composition S. Next should be R square composition S, but we have R composition S. That means it is not symmetric. You don't even have to bother going forward. The moment it breaks the symmetry, you can stop and say that this is not symmetric across the main diagonal, which means it is not commutative. Yes, so that is Cayley table and how it helps us in understanding the group. Or if we have just been given a set of elements and an operation, we can decide, at least with respect to closure property, existence of identity, existence of inverse, and commutative property, whether it forms a abelian group or a non-abelian. First of all, we can figure out whether it forms a group. Only thing is, associative property, we have to take care of it through some other way. That was Cayley table. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.